So today I'm going to move to, I'm staying within the same logic, but I moved to a very different way of looking at the computational interpretation of the logic. But before I get to that, there's a couple of remarks I wanted to make. And then we'll start into the topic of the lecture, which is SACS, which stands for Semi-Axiomatic Sequence Calculus. So I said at the beginning that I'm building a proof theoretic compiler. So I'm exhibiting the structure of the proof theory a little bit by giving you the idea of what SACS actually is. But before, there was some question after the last talk about the relation to the mode system that OCaml has. And of course, there's modes in the OCaml system which we don't have. For example, we don't have stack allocation. Okay, so we're thinking about that. We're going to have it right now. The other question was, the independence principle is very strong. So if you have something like f, which is a linear function, and you have an x, which is a linear argument, shouldn't you be able to use that to construct something over here that is unrestricted? In other words, can you use linear resources to compute unrestricted things? So you can't actually write this down because it violates this is linear, this is linear, this is unrestricted. And remember, the presupposition is that when we type an expression, that everything in gamma must be greater or equal on the right-hand side. And our relation says that u is greater than L, so we can't actually do this. But this is actually a very common idiom. You often use linear resources to construct things which are unrestricted. So what you do is that you don't construct something of Cu, but down u to L Cu. Okay, that's a positive constructor. So what your code often looks like is something like you match f applied to x with, and then the pattern here will unlock. Essentially, we'll be able to get into this mode. You construct something maybe which is actually, in this case, the result is linear, so you wouldn't actually have to do that. But you can construct something that's unrestricted, then unlock it and use it in that context. And similarly here, you can get rid of this down arrow. So by having these shifts going in both directions and being able to use them wherever you need to, you can definitely use linear resources to construct unrestricted things. And if you've written any code yet, we don't have an assignment out yet, but if you've written code, this pattern actually happens a lot. Okay. So I don't think that this is a distinguishing factor. Okay. So I mean, distinguishing factors is that our mode set is arbitrary. We have this relation between the modes. But on the other hand, they don't have as much meaning imbued to them as in OCaml, because there they refer to concrete things like stack allocation that we don't actually have. Okay. So the other remark I wanted to make is about other logics, because this system is very general, so you can embed a lot of logical constructs into it. Okay. So the one I already mentioned is linear logic. Right? And in linear logic, basically what you do is you have two modes, u, which is greater than L, and then you define bang A from linear logic as up from linear to unrestricted, and then back down from unrestricted to linear of A. Okay? And moreover, the unrestricted layer is inhabited only by this single type. Okay? So it's something like so this is the only unrestricted proposition you have. Otherwise, it's empty. That gives you linear logic. If you populate both layers with a full set of connectives, then you get something called LNL. And I wanted to mention that because it was a big inspiration for this work, which is to the Benton 95. So that stands for linear and nonlinear logic combined. So that's like a special case of what we're doing. So in that case, you have basically a full complement of these connectives here, both for U and L. And you have these shifts going back and forth. And he proves in this paper that they form an adjunction. But you don't have arbitrary pre-orders of modes. You're fixed in just to have U and L. Okay. But you can embed other logics into it. So for example, if you want to get S4 or judgmental S4, and I mentioned that this can be used for stage computation and other applications where you need a comonad, right? So then you have validity, which is greater than truth, and then you define the box of A as being up of A down. Okay, so this goes from truth to valid. And again, the validity layer in this case is usually just inhabited essentially by only this particular proposition here, or this particular type. So by generalizing it, you can express things more cleanly, more elegantly. There was a question about stage computation, how you get something called cross-stage persistence, which was unclear from the beginning. But once you start decomposing it and you can program at the V and the T layer separately, that problem has been solved. Okay. You can do monadic programming if you do Haskell. So we have a monad circle of A. Okay, and you define that by having two modes, true, which is greater than lax truth. So this is the logical meaning of that. And this is the ordinary function of programming. By the way, here and here, everything satisfies weakening contraction. So you can copy and drop as you wish. Okay, there's no structural restrictions the way they are in the linear logic part, right? Everything, each layer you can do that. And then this becomes up of down of A. And so this whole thing will be at type T, at mode T. So this has to go from T to the lax, and then you go from lax up to T. And this is a monad, and this is a comonad. And again, being able to decompose that gives you additional expressive power, because in the pure monad, this is the only thing at the lax type, but you can write other programs there, and you can still use it. So even though there's nothing to do with substructural properties, having this ability to do arbitrarily defined modes and relate them to each other by a kind of a pre-order gives you a lot of expressive power and gives a lot of explanation to things that were done slightly differently and slightly less generally before. Okay. So I just wanted to mention that because, so this is lax logic, or as you know it from programming languages as a monadic modality. It's actually a strong monad, but you know, that's a detail. Okay. Okay, so we get an explanation for a lot of what's been out there, and we only use a fragment of the expressive power. So for example, if I wanted to implement something where I had proof irrelevant stuff, okay, then instead of what are called lax here, I would have something that's proof irrelevant, and this T would be proof relevant. And then there's a theorem that if you execute something at the layer of true, then everything at the layer below can be erased. Okay, everything at the layer that's strictly below cannot influence the observable outcome of a computation at type T. So something like proof irrelevance, you don't have to code it separately. It comes for free by defining these kind of partial orders. Okay, so that's really powerful because I only have one implementation. Okay, and you can use you know, dead code analysis, if you will, just by using the mode system that you have. Okay. So not everything always has to do with weakening contraction or duplicating and dropping things. Okay, so so these things are two I wanted to mention. But now let's move on, unless there's questions on that before I move on. Yep, I thought there might be.
Sorry, can you explain contraction?
Contraction is the proof theoretic term for being able to duplicate a value. So it usually means, in an implementation, it means that you can share a value between different, you know, in different places. You can use it more than once. And weakening is the proof theoretic term for being able to drop a value. And it comes from the rules that look like this. So the weakening rule says, if from gamma I have proved A, then from gamma and the additional assumption C, I can prove A. And if you read it in this direction, it's weakening because I'm making a weaker statement here than I do here. Okay. And of course, for us, because we're, because we're thinking bottom up in terms of type checking, this is dropping this assumption. This is going to be a variable x colon c, and I'm dropping that and not using it in my computation. So it's dropped for us, but it's weakening in proof theory. And contraction is if I have gamma with two copies of A, that proves C, then one copy of A is enough. So this is contraction. And it's contraction if you read it in the proof theory way from the top to the bottom because you contract two occurrences. For us, because we read this as a program, it's either duplicating this or creating an alias, whatever this is. If this is X, you get a fresh alias to that if you want to think about it as sharing. So that's where weakening contraction comes from. Yep?
Are there any code examples for the like monadic or comonadic stuff in Snacks?
Yeah, so in Snacks, in the extra directory, there is stage 1 and stage 2. And these are an example of the JS4 kind of programming. Okay, so for runtime code generation. So you can look at those. I don't have any explicit examples of the monadic programming in the code right now. Yeah?
Maybe I missed this yesterday, but once you no longer have linear types, don't you need like a garbage collector?
If you have unrestricted and linear types together, so if you use both U and L, then you need a garbage collector, correct?
Doesn't Snacks combine up to C?
Yeah?
So there's a garbage collector.
So we'd have to implement a garbage collector if you want to collect the garbage, just like any other functional programming language. Right now, what the system just doesn't collect it, just allocates it. If I was willing to use like malloc and free, I could use malloc and free, right? But I would still have to write a garbage collector, okay? But being lazy as I am, I haven't done that yet. Okay. Yeah?
Could you explain the meaning of the channeling of the time?
Okay. So let's think about this again, okay? So this is a positive type, okay? Which means that you can observe its structure. You have pattern matching against it. And in the implementation, it's a pointer, okay? A pointer from what to what? From a value of mode K to a value of mode M. So a value of mode K is viewed as a value of mode M. That's what it means, okay? So if the mode is the same, like if this is linear to linear or unrestricted to unrestricted, it's just a pointer from something that has the same mode at both ends. It's a pointer. This thing here is a suspension, okay? So if you have something of this type, it means that it will not execute immediately because it's negative. Once you force the suspension with a force construct, it will start evaluating and give you something of type A. Okay? Yep?
When you say a pointer, do you mean a C pointer or other thing?
So more abstractly, it's an address, as we'll see today. But in the C implementation, is actually a C pointer. It has type something star. Yeah. But that's an implementation choice, of course. Yeah?
So can I think of like a downshift from unrestricted to linear as the actual value is unrestricted and can be copied, but we have like a pointer, which is a separate value, and we have like a linear, that itself is linear, so when we can only have one under the pointer.
So if you want to copy it, okay, so you can think of it as a pointer. But the pointer that you have in your hand, you cannot directly copy because that's linear. But once you expose the underlying data structure, then you can copy that. Yeah. Okay. We'll put up a homework assignment. We're a little bit behind because we changed our order of lectures and everything. So, but it'll come out sometime soon, and you can actually enjoy now being able to do nonlinear programming, right? Now the pain is mixing linear and nonlinear programming. Okay. Okay, but now I want to come to a new topic, okay, which is how do you now, we think about this as being store, and one of the things we want to think about is that when you use a linear value, you can deallocate it or you can reuse the store that's being used. Now, in order to be very explicit about that, you should make store explicit. Now, normally when we think about making store explicit, we think about something like separation logic or some imperative programming language, right? And I'm compiling to C, so that's not totally the wrong view. But I want to find a higher level explanation. I want to stay at the logical level and still give you a good explanation of what store is, right? And this was where the sequence calculus comes in, okay, which shouldn't be a surprise to Paul there, but I was surprised the way it worked out. Okay, so let's think about this. So the store model I want in today's lecture is actually I'll start over here. If I have a type nat, the way we've defined nat as unary natural numbers, okay, I want the layout to be like this. I want to think about it as here being either 0, and then this is unused, or it should be something like successor, and then maybe this is a pointer to the next natural number. Something like this, okay? Or maybe even, okay, this is a pointer to something which has size 0, which is the value of type unit that I have, right? The unit value of type 1. So, you know, which one you think about is a matter of optimization, but I want some very simple. So a list would be something like this. It would be a little bit wider because you have a const cell here. And then instead of laying it out flat, you have a pointer to a pair. And then the pair has 2 pointers. One would be to a natural number, and the other one would be to another list. Okay. So I'm not yet thinking about a flat layout, just this kind of pointer-based layout. Okay. So how can we type something like this in a programming language so that it corresponds exactly to this? Okay. So the way I'm going to start is, so if I have a pair, pair is kind of easy often to think about. So if I have a pair, okay, that should have type A cross B, okay? Now, normally I put expressions here, I put values here, okay? Now I'm not going to do that. What I'm going to put here actually is addresses, address A and B, okay? And that's because in a pair, I want it to contain 2 addresses, right? So I haven't explained what addresses are yet, but that's what I'm going to do. But what we can say no more, because we can say what should be the type of A. Yep. I chose these letters extremely cleverly, okay? I know that you wouldn't have thought of that, but okay. Okay, that would be it, right?
Wait, the A's and B's are addresses, but the addresses are not part of the type system?
No, they are. They will be part of the type system. You'll see. But the point is that this rule would describe the typing of a cell that looks like a pair of 2 things of type A cross B. Can we buy into that for the moment? Okay. All right. What about the unit value? How would I type the unit value? Well, I would say, okay, this 1. And do I need anything on the left-hand side? Nope. And what about a sum? Now we have to think. So if I have something of type L colon AL for some index set, okay, how would I describe the contents of a cell of this type? So let's look over there at the picture. For one of the L's, yeah. Yep, it would be K. So these are my tags. And then what would it tag? Another address A. And what's the type of A? A sub, which one? A sub K, right? Because I pick out this one here. And this one would be the rule. And this, I would have to require that K is in the set, otherwise this doesn't make sense. Okay, does that rule make sense? Okay, that's what I would need to type these memory cells. Now, let's look at the logical side of this, because I always like to go back and forth between logic. And so if I look at logically, this just says, if you have A and you have B, then you can prove A cross B. Does that make sense as a logical axiom? If this is conjunction, this makes perfect sense, right? It's an axiom. It's not an inference rule the way we're usually used to, because there's no premise. Okay. Okay. This would say we can prove 1 if you have nothing. And in fact, this rule looks very linear. So if I want to emphasize that, I would say, well, this is a linear form of conjunction, right? Okay. This rule would say, if I do it logically, and this is a binary sum, which I often do, okay, it would be 2 rules. How we prove A or B. Okay, so one way would be to prove it from A. And the other way would be prove it from B. Okay? So Hilbert would be very happy right now, right? Because I take all these net reduction inference rules and I turn them into axioms, right? So, so why do we call it semi-axiomatic calculus, right?
Because the other half of the
Because the other half has to be inference rules, yeah, okay? So in fact, we counted them up, and they're exactly half of the things are rules, the other half is axioms, okay? Okay. I didn't do the shifts yet, but they're actually, turns out to be not very interesting, but okay. So now what does it mean to compute on them? So these are kind of replacing the ways of constructing values. And previously, the elimination rules eliminate values. And here, they will read from memory. Does it make sense? You just read from memory now. So for example, if I have a memory cell which contains a pair, okay, let me call it C, to emphasize that it's going to be bound to an address, which references a memory cell. And that contains A cross B, okay? Then I should be able to read from C, okay? What do I read?
The pair being
A pair, and what do I do with that pair?
dereference the actual.
Destruct it, how do I destruct it? Pattern matching, right? That's what I've been doing all along. I'm not going to change that. So I pattern match against the pair x, y. And I'm going to write not E, but I'm going to write P for these programs. And this is going to have some type on the right-hand side. Okay. So if I presented the linear rule, what happens to the C? It disappears, right? Because I'm reading memory cell, this is linear, it's no longer there. I can no longer read it again. But what do I get in the context instead? X of type A, Y of type B, and then I check P, and whatever I have here is just carried over. Nothing changes over on that side. Just like in our usual typing, right? The right-hand side does not change in the pattern matching rule. And it will make sense? Now, what does it mean logically? Okay, if I erase over here, logically, it is the following rule. If I have A cross B, and I'm trying to prove gamma, which I'll write as C here now, then I can prove C from A comma B instead. Does that make sense as a logical rule? Purely logical? Forget about the intuition about memory? Makes sense, right? If you have A cross B, well, you can get the two components of that pair. Okay. All right. So you can probably figure out the rest of the rules here. What if C, if I'm trying to read a memory cell of type 1, I read C, then I match against the unit element and I get P. This will have some type over there, which I don't care about. And then I get nothing here. And P would have to have that same gamma that at the moment I don't care about. And I forgot to say something here. There might be other assumptions, gamma, right? And those are not really affected by this operation. So, and here, some assumptions, gamma not affected, and I get just gamma here. Okay? And now finally, if I'm trying to read from a cell, which is a sum type, L colon AL, or some index set capital L, I'm reading from C. Okay, how do I read from C? I have to have a branch for each possibility. L of x goes to P sub L, and that has type gamma if what happens in each branch? I get the same gamma. What do I get in the branch L? So this will be for every L in L. X is of type A sub L, and I have to prove what typing over here? PL is of type gamma, right? The gamma is the same everywhere. This one is the same, this one is the same, because I don't know which branch will be taken, so I have them all the same. And I have to do this for every possible branch, okay? Are we good on this? Yeah?
Can you re-explain that rule above?
This one?
No, on the left, right above or one that you just finished?
This one here?
No, the unit rule.
Oh. This rule?
Yeah.
Okay. Okay, so if a memory cell contains the unit element, I can read from that cell, just like we match against something of that type in the previous language. It'll have to match the unit element. That's the only possibility. Then I'll continue with P. And for that to work, P has to be well-typed and has to have the same output type over here. Yep?
Can I just make sure I understand the bottom rule correctly?
The what?
The bottom rule?
Yeah?
Okay, so essentially what you're saying is, if you want to make sure that your program where you're reading C and matching on its constituents
Yeah?
is well typed, it has some type gamma, then it should also have worked if you, instead of having C, had whatever constituent C had, in this case X. Then it would continue to be well typed, and the type would be the same as all others.
That's one way to think about it.
Okay.
Yep, that's correct. Or you can think about it as, if I'm writing a program, and I don't know if I'm looking at a con cell or a nil would be like this. This would be like that. I have to account for both cases, what might be in the memory cell. It could be a cons label, it could be a nil label. And the type of the other one, the other part of that cell, depends on what the tag is. If it's a cons, it's going to be a pair. If it's nil, it's going to be unit. Okay? And I have to account for all possibilities.
I mostly just wanted to make sure I got the order of the inference rule right.
Yes, you did. Yep. Okay. So this all looks very nice. And it all has completely logical rules. The other one says if I have gamma together with 1 and I prove C, then I can use gamma to prove C. And the other one is a binary rule by cases, which says that, get rid of this, if I have gamma and I have A or B, I'm trying to prove C, I just have to distinguish the two cases of A and the case of B. Okay? So from a logical point of view, these are perfectly respectable rules. They're a little bit weird, and I'm surprised actually that nobody before us had this kind of a system. But the system is that these rules are in something called the sequence calculus. So this would be called the tensor left rule. This would be called the plus left rule. This would be called the one left rule. But the usual right rules here are replaced by these axioms instead. Okay. So half the usual rules, which I'm not showing you because I'm not showing you Genson's original sequence calculus, are replaced by these axioms. Okay? Make sense? Buying into that? Okay. Now computationally, how do we interpret that? The way we want to interpret this judgment, okay, in gamma, okay, it's actually not like that, sorry, it's this one. In gamma, P, okay. So this right-hand side is going to be, we have to change our minds about this at the moment, but these are all addresses, and the program P can read from them. Okay? All right? So now, there's two rules in the sequence calculus in general, okay, that you will need in order to get computation started, which is cut and identity. Okay. So what is the rule of cut? Okay, let's see, where did I put this? Okay, let's put it here. So let's start with a logical rule, because I'm not going to change that. It looks like this. If I have delta and gamma, and I'm trying to prove C, what I can do is I can devote some of my resources to proving A. That's if the logic is linear, these things have to be used exactly once, so I have to split my context. And then over here, I get A as an additional assumption while I try to prove C. Okay, so in mathematical proof, this is introducing a lemma. So you prove a lemma A first, and then you assume that lemma while you're trying to prove the conclusion that you want overall. Okay. So the question is, what does this have computationally? What is this thing? Okay. So, yep.
But doesn't it become a bit trivial now if you have that your writing production are all axioms?
No, 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 you might think that, and I thought that, but no, it doesn't become trivial, okay? The question is if this becomes trivial now that we replaced half the rules by axioms, and the answer is no, okay? Rarely can I answer a question so definitively and so easily, okay? I just no, okay. All right, so let's think about this computationally. Okay, so we have some resources, and now these are actually describing a current state of our store, okay? And I know what happens over here. Okay, so here I'm making a new assumption. What that means is there has to be a new cell in memory while this program Q here over here executes, right? Because I'm adding something to the context. We already agreed that these should describe memory cells, so X should be an address, and Q can read that address. So what does P have to do in order for this now to work out? So P is going to be some program over here. And P is going to use delta. But what is P's job in this rule? If this is Q is going to read from it, what does P have to do? You'll have to, well, the rule has to allocate it, but then P, when it runs, has to do what? It's going to have to write to it. Somebody has to write the cell before Q can read it, right? So what will happen is we'll say P will write to X. We'll write it like this. So normally when we type expressions, the right-hand side doesn't have an address. But here the right-hand side of the program has an address. So every program that runs has a destination where to put its answer. So rather than returning one that we were used to when we run expressions, we're given an address and we have to write to that. That's our whole job. Okay? And then this, after this is done, this can run and can read from X. And its job is to write to some address C of type capital C. And then here we say a cut, because that's the name of the rule. And we create an X, and then we run P, followed by Q. So just a small digression. Originally, we developed this for a parallel semantics. And then you run P and Q in parallel. And if P hasn't written to X yet, then you will have to block until P will write to it. So the variable X is actually a means of communication between P and Q. Okay? So this is actually called in functional programming, it's called futures, if you've heard that term before. So this actually starts the computation of Q immediately, and P is a future that can execute in parallel. And if Q needs it, it might have to block until that value becomes available. Okay? But in the implementation, we're still months away from having that. So right now, we run P first. That guarantees to write to here if it finishes. And then Q can definitively read. It never has to block, because we'll know that this will have finished. So we run these sequentially. Okay? And so cut is an allocation. Okay? So what is the other rule that we need here, which is the identity rule? So the identity rule logically says, okay, if I have A, I can prove A. So this is the identity, and this rule here, just so you see the terminology, is called cut. Okay, so let's put things in here. So this is like a Y colon A, or let's say B colon A. That's bad. Okay. All right. Okay, I'm running out of analogous letters. So this is a B colon A. This is an A colon A. Now, what is the process that I'm going to write you have to do? What's its job? Let's think about that. It has to write to A, and it can read from B. So what does it do? It moves things, right? So I'll write identity, but it writes from whatever B contains and writes it into A. Okay? So this is a move. And this here is an allocation. Okay, are we good on that? You have a question? Yeah?
This might be really silly,
Yeah?
but I might as well ask.
Yeah?
You said cut is an allocation.
Yeah.
Where is X freed?
Hmm?
Is X freed, and if so, where?
Okay, yep. So X is bound here, and the scope is P and Q.
So it's freed after Q?
Hmm?
It's freed after Q executes?
No, X occurs in P and X occurs in Q.
That's all you're saying?
And it's bound here, so it's not free outside.
Okay. No, I meant freed as in like unallocated.
Oh, free as an unallocated. So the cell doesn't exist before you run this. Okay. Then it will get allocated here, and it will be allocatable, be empty. When you run, P will write to it, then Q can read from it.
Yeah.
When Q is done, okay, then now it depends. Okay. You can no longer refer to the variable X, but whether the cell is actually still allocated or not depends on what Q does. For example, if A is type nat and Q takes the successor of it, okay, then that cell that was allocated is still alive because now this destination will be the successor of a pointer to that. Okay. If this Q here does a case over it and decides whether it's zero successor to take, let's say, the predecessor or implement plus, then it will be deallocated when it's being read. So that's not a silly question at all. Okay, that's actually a very deep property of the system. Yeah?
I think this one actually is a silly question.
Okay.
What do the double colons mean? Is that like this syntax you made for showing the address? Or
Okay, so I want to use a colon here. So if I write colon here, there's too many colons. So I write double colon instead.
it's not a type.
Hmm?
It's not a type.
No, this says this is an address of type C with a destination for this process. Okay. So it is a type in some sense for this process here. So this process is typed in an environment where I have delta, gamma, and that C on the right-hand side. But they're distinguished because this is something I have to write to. And these are things I can read from. Okay. In fact, if it's linear, I must read from them. Right? Yeah?
So if you evaluate P and then Q sequentially, does
Yeah.
it look a lot like the net finding?
Yeah.
Could you model this with a lambda abstraction instead?
No, that would have to introduce an arrow. I don't want to introduce anything like a function here. Okay, so no, I don't want to model this with an arrow. But it is like a let binding. Right? You could have a let binding like syntax for this. But it's a little strange. Well, okay, that's because let binding suggests that P returns a value, but it really doesn't return a value. It writes to the destination. So I think it's different, so I'm hesitant to use let binding syntax. Okay. Okay. Now we have to change our minds about these things. But only slightly, luckily. Why do we have to change our minds? Because that judgment we wrote down there, when we started, this judgment doesn't have the right form, right? Because on the right-hand side, we said the cell has this type if it contains an A and a B, and these are being used. So now I have to change this. How do I change this? Any thoughts? Okay, so all the constructs so far, we allocate, okay, or we read, or we move. Right? These are the only three things we have. So how do we write? Right, this process P here, it will have to write at some point to the destination, right? So what does this rule then become? Can you see that? I'll erase the logical rule because we're all convinced that this is all purely logical, right? So let's figure it out. So we write, and so we have A cross B, and we have a destination C that we have to write to. And on the left-hand side, we have A colon A, and we have B colon B.
It moves A and B into the pair A.
Yep, so it writes, right, to C the pair AB. So it doesn't actually move because it doesn't read the content of these cells, but it writes the address A that it has into the first component of the cell and the address B that it has into the second component. So the move here is different because that move will actually read what's in B and move it over to A. But this will just write these addresses into that cell.
A move is a physical movement of data in memory.
Yep. So we read from one cell and write it to another one. Okay. And here, we don't actually move the data from these cells. We just say, okay, write the address A and B into that cell. Okay. So now, we can imagine what this is, right? This just says, without any context at all, I can write the unit element, into the cell C, the unit element, and that will have type C of type 1. Okay. And this one here will say, if I have an A of type A sub k, then I can write into the cell C the tag value k with destination A. If C has that sum type. Okay? Okay, that's it. That's the whole language. Okay. And memory is now explicit. Memory movement is explicit. Reading and writing is explicit. And logically, it's just a very simple sequence calculus. Okay, I haven't done anything fancy. Okay. Okay, so actually, what do we have? Let's see, where should I put this? The logic of rules. I'm just there to convince you I know what I'm doing. Okay, so we get rid of those. Okay, so at the level of programs, P, okay, what do we have? We have write to a destination, okay, a value V. Or we have read from the destination, a value and match it against some continuation k. Or we have move to A from B. Or we have allocate an X and execute P followed by Q. Okay. So this is move, allocate. And what are the values? Values V are pretty easy. It's a unit value, or it's a pair of two addresses, or it's a tagged address. And the continuations just match against those things. Match against that, or we match against the pair, or we match against the sum. Okay? Does that all make sense? Okay, pretty simple language. We don't have very many constructs, right? What I really like about this is that we just have these things, right? So it's a very small language. Now, the interesting thing will be, if you get about today, if you add the negative types, you don't add anything more than you already have. Okay, that's actually surprising, but it's true. Okay, let's see. So if we're good with that, okay, but I'm taking questions. The easiest way to write programs in this language is to compile a program from our original language into this one, okay? Because we're breaking things down into very small steps, okay? It's not so easy to write these programs by hand, but I have a compiler and I have also a printer, so I can show you what the outcome of compilation is, okay? Yep?
I'm not sure if this question is in scope, but what makes these rules the sequence calculus rather than like natural deduction?
Okay. So in a sequence calculus, you have access to apply rules directly to things on the left-hand side. In a natural deduction, you do not have that. So in natural deduction, you have introduction elimination rules, but the only way you access the context is by using a variable. But here, you can directly work on your assumptions. Okay. When you,
Sequence calculus lets you write stuff on the left
Are you talking about now the operational interpretation of the sequence calculus, or?
No, just purely syntactic.
Okay, so the actual sequence calculus, okay, these axioms that I raised by now, okay, are actually also inference rules. So you have rules on the left and rules on the right. Okay. And so far, I've taken all the rules on the right and I've turned them into axioms. The rules on the left stay what they are. Okay. But it's still a sequence calculus because you move up on the left-hand side. You just have direct access to your environment because you want to directly read from memory. Okay. So it has a closer in character to a sequence calculus than to natural deduction. Okay, other questions? Yeah?
Are you planning to talk more about why, if you add all the negative types, you don't get anything else?
Yes, but I'm not sure when. I'm either today or tomorrow. Yeah, I will definitely talk about that because it's actually something that also surprised us, but yeah.
Can you repeat the question?
The question was if I'm going to talk about how the negatives work and whether they fit, how they fit into the scheme, and the answer is I will. I just don't know if I'll get to it today or not. Because I want to actually now write code in this. So there's two ways I can do this. I can show you how the rules, the translation rules, from natural deduction to this calculus, or we can live code. So, okay, let me do both. Okay. But by which I mean I'm going to show you some translation rules, but not all of them. So I'm going to show you part of the compiler. By the way, the correctness of the compiler is essentially proof-theoretic proof. It says, how do you translate from natural deduction to the sequence calculus? Okay? This is a proof-theoretic question. And the answer to that is my compiler. Okay? So, all right, so we're sending out, the way we're going to do it is this. Originally, we have in gamma, E has type A. And I'll think about it linearly. It doesn't matter. Okay? So I'm going to compile this in the following way. These variables here stand for values. Now, the corresponding variables over here are going to stand for addresses. So no longer values, but addresses of memory. Okay? I'm going to translate the expression E. But I translate it having in mind a particular destination for the program that comes out. So I translate with respect to a destination D. And when I've done that, this program P here will write to the destination D a small value over there, a small value of type A. Okay? So I have to make this part of the translation explicit because there's no destination here. I'm returning a value. But here I have a destination. So I have some place I have to write to. So let's start. Okay, so if I have a pair, E1, E2, and I'm going to compile this down to a program which will write to a destination 2 in this language, how would I do this? Yeah, you have an idea? You start with a cut. So we start with a cut. And let's say we create some new destination D1. Okay? And now we have to have a process that writes to D1 and a process that reads from D1. What's the process that writes to D1? It's going to be the translation of E1. And what destination do I translate it with? D1. Right? Because it's supposed to write to D1. Okay? That's it. Now, in the next line, I write the program that will read from D1. What will that program be?
D2.
We introduce D2. The simplicity of the compiler is a big feature of this thing, right? So, and what does it, how does it compute? It's a translation of E2, and what's its destination? E2. Okay. And now when I'm done with all of that, what do I do now in order to satisfy my requirement of the translation, namely writing a pair to destination D? No, not ID, actually, because that would read from these cells. I don't want to read from these cells. Yeah? Yeah? write to D the pair D1, D2. Yes? I think 90% of you could hack up the compiler right now, okay? And it might be more correct than mine, okay? But let's see what happens if I compile the corresponding pattern matching construct. I'm running out of board space. Let's see what we have here. Okay, we've taken care of these. So I'm only showing you 3 rules in the compiler. Okay, to give you a flavor. All other things are similar. Okay, because there's so few constructs, there's not much you have to do. Okay, so how do I compile a match E with the pair XY and then E prime. And the destination for the whole thing should be D prime. I'm using D prime here because it corresponds to thing actually returned. Okay, how do I compile that? What do I have to start with? I have to evaluate E. How do I do that? Cut. I create a fresh destination D. And now I have to have a process that writes to that destination. What is that? Translation of E. With what destination? D. Okay. Now I need to write a process that uses that cell. How do I do that? Read. What do I read from? D, which I've allocated here, right? And then the read for a pair says I get X and Y. And now, how do I translate E prime? Well, I translate E prime, and what's its destination? The original destination, right? Because this whole expression is supposed to write to D prime. Well, that's what E prime is going to do. It's going to write to D prime, right? If I translate with that destination. You see this? Right? Okay, I just want to show you one more rule. Okay. How do I compile a variable? A variable X with destination D equals. No, I actually don't need cut. Cut is the default answer, but in this case, it turns out to be not the default. Yeah? Yeah, so we move with the identity 2D X. That's it. The variables turn into the use of the identity. So they will read from X, whatever X contains, and move that into a destination, and thereby writing to the destination. Okay?
So this is using a variable.
Yes. That's using the variable. Okay? Yeah?
I'm a little lost on the motivation of this compilation. What does packet a program in a target language bias?
Oh, because
Can you repeat
this
the
is.
question?
Hmm?
Can you repeat
So the question is, what does this bias? Well, this language here, you can translate very straightforwardly to C and run it. So what it buys us, we get a compilation for this program here that makes memory explicit, and we can represent so these A and Bs as addresses in memory on the heap. And they will read from the heap. This will write to the heap. This will move from one address to another. This will allocate something in the heap. When you write this down in Nash reduction, who knows? You have to write a compiler for it. Well, I did. This is it. Okay. That make sense? So let's see the result of compilation in action. Okay. Like I said, it's not so easy to write code because I wouldn't call it a code explosion, but like one pair corresponds to a match. There is some expansion going on there. Yeah, you still have a question?
Yeah, so like if I'm translating my variable uses as these moves, am I gonna have a bunch of these like superfluous moves?
Yes, you do actually.
Okay, and then
Yeah, but you get rid of them. So there may be superfluous moves, So the compiler has one single optimization that, no, actually two optimization. One is the following. If you have a cut and you allocate an x, and then you move from to x from y, and then you have q, and this q can mention x, right? Then you optimize this into q of y. Okay, so because this just moves from y to x, and then it executes q reading from x, you might as well do the move first, like statically, and then just read from y instead. No need to do that allocation. So that's the one optimization that the compiler did from the outside. The other one is that sometimes you don't need to allocate a fresh cell. If it's linear, you can get rid of it and maybe reuse. You can reuse something that you have read before. But that's a more complicated optimization. This is the proof-theoretic optimization because in proof theory, the slogan is that cut and identities are opposites. So if you have a cut with on the one side and identity on the other, then you can reduce that. So it would look something like this in logic. If I have delta and gamma, and I'm proving C by using, okay, in this case it would be A. From A proves A, and then from gamma and A proves C, okay, then I can reduce that to just take this thing over here, okay. So in any proof theory text, you will see that, well, cut and identities are opposites, but what that means is that this kind of thing reduces to just essentially this proof here, that proof of A, because it's the same as a conclusion. And if I had written it slightly differently, that similarity would be even more obvious. Okay, so I do that optimization. I felt good about it because it's proof theoretic. I don't have to apologize for it the way I have to apologize for other optimizations. Okay. By the way, the discovery of all of this is not in the way at all that I presented here, right? So, like, we designed the semi-axiomatic sequence calculus for something totally different, having to do with session types and asynchronous communication. Then, hey, look at what we have. Yeah.
Does linearity make it easier to convert into SSA?
Can you repeat the question?
Does linearity make it easier to convert into SSA? Probably. So we leave this detail to C. But C doesn't know that these things are linear. So
I guess you're targeting.
if I'm writing my own compiler, eventually I might have to. Then I would probably take advantage of such properties. Yeah?
That last example where you were evaluating X, why are we using cut first?
In this example here, the variable x, this, because we already have x, we already have a destination, so why we need to introduce a fresh destination? So the cut introduces always a fresh destination.
So X is already allocated.
X in the translation, the variables of my source language will become addresses here, so it has already been allocated by the time I get to that. Yeah? Yeah?
Would you have to change the rows here if you wanted to change the data layout?
Yes, that's tomorrow. Yeah. So I would have to change the rules if I want to change the data layout. Actually, let me backtrack from that. No. No. I just have to interpret them differently. The rules are actually the same. Yeah?
Can you do things like cut elimination to save memory?
You could. But the implementation doesn't do any of that kind. Okay. Yeah. It's an interesting thing to consider to what extent you want to do cut elimination. For linear things, it's pretty free because you don't have to do much copying. But for nonlinear things, it could explode the size of the code. So you could do something like that. Okay. So let's write some code. So type, my favorite type, the only type. Oh, no, wait, I'm doing a new type, binary numbers. Okay, so they're going to be at some mode M. And it's going to be a sum of, okay, I could have a bit 0 followed by another binary number, which is guarded at the same mode. Or I could have a bit 1, which is followed by another binary number at mode M. Or I could have E, which means the empty bit string, whoops, followed by 1. So this is, and if you've looked at the homework, this is called the little endian representation of numbers. So the least significant bit comes first, and epsilon represents the empty. Okay, so now I want to write a very simple function because I want to get the compiler cranking up, okay? So let's say increment on binary numbers. So I declare increment, which takes an x of type binary number of m, and give me a binary number of m. Okay, define increment x equals match x with. It could be bit 0 of some x. What does increment do in that case? Bit 1 of x. Okay. Or it could be bit 1 of x, and then bit 0 of, okay, increment of x. Yes? Okay. Or it could be 0, in which case I return bit 1 of, oops, of 0, right? That's a representation of 1 in this binary system. So if you think about little endian form, that seems to be the correct thing, right? Are we okay on this? So now to generate any code, here's something new which I haven't shown you yet, which is an instance declaration. So I have to define a concrete mode. So I say mode, okay, I like this to be linear, so let's do that. And then I say an instance, please compile an instance of increment at this mode. So that will check that, first say, well, that's a valid mode for the function and also generate code for it, okay? So let's use that. Okay, snacks.
You probably need to
Oh, save it, yes, thank you. You see the star from there? Okay, okay, good. Lecture 4.adjoint. Okay, everything type check, and it produces a whole bunch of files. And the whole bunch of files, they're interesting to look at, but we only want to look at right now at the Sachs version here. Okay, and then we'll later look at the closure of the Sachs version. So let's look at the Sachs version first. Okay. Lecture 4.adj.sax. Okay. So this is more or less, except for this one optimization that I've talked to you about, this is a straightforward translation. Probably cannot quite see that in the back yet. Okay, here, of what I had before. Okay. So we have a procedure to increment. Okay. And it takes the destination. So the convention is the first argument is always the destination. Okay, just to make things sane. It doesn't return anything. There's no return value. And I give it x, which is a binary number. So we read from x, and we distinguish three branches here. If it's bit 0, then there's a variable that was not apparent in the original source because we did nested pattern matching, so it gets some new name, $1. Then we read from $1 because we dereference a pointer. And then we allocate a new cell called $3, which has type down L of bin. And then we write that address from here down in that destination. And then we write to the original destination, 0, the tag value B1 of $3. Does that kind of make sense? Yeah?
Would it be possible to, like, pass this level, I guess, into whatever target language you want? Optimize this into just changing the B0 tag into a B1 tag?
Yes. You were just 3 minutes ahead of me. Okay? So then in the B1 branch, okay, I do pretty much the same thing except that I have to make a recursive call. So I have to allocate a destination for the recursive call, which is a destination. I call increment with the destination. I read what comes out of that, and then I put a tag B0 on that. Okay? And in the case it's 0, right, what does this do? Okay, so we read the unit element, then we allocate something fresh, and we write the unit element into that. Then we tag the unit element with E. So we have 0, E of unit element. Then we create a pointer to that, and then we write B1 of that thing. Okay. So the components of the file that we had before, lecture 4.adj, okay. So I have to do the brackets, I have to do the unit value and the 2 tags, and this is what this does, okay. So this is without the reuse optimization. So if I use the reuse optimization, I get, for reasons that the naming convention is, okay, I get this function. Okay. And so here what happens is, can you see that in the back? No? Okay? All right. So we read from x, we get B0 of 1. We read from 1 the pointer. So at this point, we have read x, and we have read 1. So instead of reallocating something fresh, we're reusing that $1 we just read. And then we write $2 into that, and then we write B1 of that into the destination here. And in the second case, we reuse as well this $5, which we read from here, and the $8, which we read from, this is x, which was one of our inputs. We make a recursive call, and the destination is the same as for the original call, okay? As this x, sorry, the argument of the original call. And then we write, but there's no allocation for the B0 and B1 at all. Everything is reused. We need to allocate when we come to the 0 case because, well, we need to create out of 0 the number 1, and the number 1 is longer than the number 0. So we only create something fresh if you go all the way to the number, the carry goes all the way to the end, and we have to do something more at the end. Everything else is just flipping bits, right? We don't do anything else. And this is like without any, this is only using this general purpose idea that if you're in linear logic, if you read something, you can reuse it. And there's no really much smarts in here. And one of my students, Daniel Ng, who is actually starting to work at Jane Street pretty soon, in his senior thesis, proved the correctness of this optimization, okay? Okay, does that make sense? Okay. So now let's look at what this looks like in C. Okay, maybe it should do this almost side by side, but I don't need to because, okay, so is there anything fancy here? So I translate every source type into a C type. Let's see. Yeah. So there are no closures here. This stuff is dead code. I have code to print, which is generated in a type-directed way to print these things so I can see the output of my computation. Okay. I forward declared everything because I have arbitrarily mutually recursive functions. And so here's the function x0. Let me make a little more room. Okay. So this $0, by the way, is there because if I have also an unrestricted version of the function, it will compile to a separate piece of code. Because that cannot reuse, the linear version can. So I have this kind of like branching that lower down. Okay, so what do? We switch based on the tag where x is. That corresponds to reading x. And then if the tag is B0, then I have to read now from $1 and get $2. How do I do that? Well, I retrieve the pointer, which is the second pair of this tag value, the second component of that tag pair, which is at x. I follow that pointer. Okay, that's that dereference. Then I reuse that, and I translate the reuse just to an assignment. So C will compile this assignment away, of course. And then I have to write to destination 3, and that just is an assignment to the address where that is. Then I have to write the tag, and that's also just like this. It's done in 2 steps because I need to write the tag. The first component of the pair, which is the tag, and the second component of this pair is the pointer. So this 1 write becomes 2. And then I have to break, otherwise C will be very unhappy. Okay, bit 1 is kind of similar. And in the case that it's 0, there's some allocation going on. So here I allocate 1 word, essentially, because that's a pointer that I need to allocate there. So you can see it's almost 1-1 between the SAPS code over here on the right-hand side and the C code over here. And that's because all I'm doing is I'm reading from memory, I'm writing to memory, I'm moving things between destinations, and I'm allocating. Right? This is all the language has, right? And it turns out that the C-type system is good enough so that I actually can represent these things as C-types. Every one of my source types becomes a C-type. Okay? It's a little bit ugly to read, but if you want to see it, okay. Actually, not here. Okay, so here I just use sorry. In this version, I'm using a universal type of value, which is a union between a tag, a pointer, and then for closures, I have environment and function pointers. Okay, but we don't use that in this example. Okay. Okay, so that last step to see is actually kind of simple. But of course, I don't have a main function in this example, so there's no, the main function itself doesn't do anything. Okay. Okay, let's go back to our example. Lecture 4. But you can imagine that that isn't a very difficult thing to add, right? If I have a main function over here, it'll compile it to the appropriate main thing. So let's do a couple of things. One thing I wanted to do, the language has some features I haven't talked about yet, but which I think are really cool. One is which is subtyping, okay? So if I were interested in having binary numbers but without leading zeros, okay? It makes it very easy to compare a number to 0 because it has to be E. Right now, comparing a number to 0 has to be a recursive function because it could be bit 0, bit 0, bit 0, bit 0, E. Okay, that would represent 0. So sometimes it's nice to do that. Okay, so how do I do that? So I would say a standard number, so one without leading zeros, is a choice between, it could be B0, and then I could have another standard number. Okay. Or it could be B1 and have a standard number. And we'll have to fix that in a minute because this doesn't work. Okay. So how do I fix that if I want to avoid leading zeros? What do I have to change here? I don't know if you can think about that in real time. Yeah, you have an idea?
We can suppose there is always a 1 in front of the sequence, an implicit 1.
Yeah. So how do we actually enforce that by typing?
Oh.
Yeah? Yeah, it goes in that direction. We can try to do that. You have another idea? Yeah?
Maybe just have start root at 0 and then make the argument of 1 be a binary.
Excellent. So we can't go back to binary because once we go back to binary, we lose all control. But it's very close. So when we have a bit 0, it's not a standard number which follows that, but it has to be a positive number. Does that make sense? It cannot be 0, because if it were 0, then we would have bit 0 off a number which represents 0, which would be incorrect. After bit 0, the rest of the number, looking from a little endian perspective, has to be positive. Yes? Does that make sense? So how do we define the positive numbers? Oops. The positive numbers are, well, they look the same almost. Okay. So bit 0 of something is positive if the thing that comes after is positive. Yes? Bit 1 of positive is positive if the thing that comes after is standard, right? And is 0 positive? No. So we just have to delete that possibility. Okay. Does that make sense? Yeah?
So in essence, what you're basically,
Yep, exactly. That's what these two mutual recursive types encode. Okay, but I can't just write it like that. Okay, and now I can say, well, another type that increment should have should be if x is a standard number, then hopefully if I played my cards right, the output should also be a standard number. Does that make sense? Should that be the case here? Could we ever introduce leading zeros? Well, the only thing we introduce is B1 of E. That doesn't have a leading zero. So it should be the case that this is true. In fact, we should also be able to say that the output of increment should always be positive, right? Because we increment any binary number, right, the result should be positive, right? So let's see if our type checker believes me, okay? Yep, it does. Okay, so that passes, okay? So sometimes this kind of additional typing, oh, by the way, I should mention something. So if you're used to programming things like OCaml or something like that, right, you might be used to putting things like this into here, right, into the definition of the function. But I can't do that because once I do that, I fix the type, and I really want to have the opportunity to assign multiple types to the same function. So I have to separate the definition of the type, the declaration of the type, from the definition of the function. I'm going to take myself 5 minutes, okay, to implement decrement. How do I decrement? Whoops. I'm going to write the declaration second in this case. So I have a case for B0 of x. What happens there? Is it B1 of decrement of x? Does that, whoops. You have to introduce a borrow, right, in this case. If it's B1 of x, what do I do? Then I should just become B0 of x, right? I don't have to do anything fancy. Are we good? And what if it's E? Well, I can either say that's an error, or I could return just, if you decrement 0, you get 0 back. Okay. Okay, so declaration for decrement would be, it takes a binary number and gives you back a binary number. Let's check that. Oops. Okay, that checks. So can I also give it the declaration? Decrement takes a standard number and gives you back a standard number. No? Okay, very observant. Why not?
Because B1 0 or B1 of the string B1 goes to the string B0.
Yep. So let's see, the type checker notices that, I believe, unless there's another bug. Okay, so it gives you a type mismatch. It says right in this place where you turn B1 into B0, okay, like you suggested. We synthesize the type standard of M, okay, and we're checking at the mode positive of M because underneath the B0, the thing has to be positive, right? And in fact, if you take B1 of E and you run this algorithm, you get B0 of E, which is not in standard form. So it puts you exactly to the place where you made the mistake, okay? And so one of the reasons I came to this because I ignored that and I had this decrement function. And what happens is if you have a loop and you decrement and you check against 0, and the check against 0 is it's E, okay, you will get into an infinite loop because it'll be B0 of E, and then you decrement that, it will still be B0 of E, and so on, and it will never do anything. Okay, so we need to fix that. So How do we fix that?
Match against X.
Yeah. So it's in this case, right? No, in this case, right? The second case here. We have to match against X. So we say, well, if it's B, well, okay, if it's E, it's one thing. And if it's B1 of B0 of X, it's another. And if it's B1 of B1 of X, then it's a third possibility. So what do we do in the first case? What do we do here? We make it just E, right? What do we do here? B0 of B0 of X. And what do we do in this case? B0 of B1 of X, right? Okay. Now let's see if the type checker will be happy with that. Okay. Okay. So now we know that it takes a standard number and gives you back a standard number. Okay. So there will be no leading zeros. So this is a little bit besides my main point of my lectures, but I still wanted to show you because I think it's cool. Yeah?
Can we not get the wrong answer for B0 of E? Because then we get B1 of deck of E, which is B1 of E.
B0 of E is not allowed as an input when the number is standard.
Right, but for the, say we have binary numbers.
Yeah, but binary numbers only ask the output to be binary.
Yeah, but don't we get the wrong answer, not just a wrong representation?
Oh, yeah. So I better erase that first type. Okay. It type checks, but this is the wrong. Okay. Yeah, sometimes type checking doesn't always give you everything. Okay, good point. Excellent point. But wait a second. Yeah, I think you're right. Oh, you need to know it's a standard form for this to work. Otherwise, it won't. Very good point. Excellent point. Okay. Okay, so what I wanted to do tomorrow is two things. First, I want to talk about the negatives, which I left out today because they take a little more discussion, but they work extremely nicely in this. The only thing I don't like is the compilation to C eventually, but because we have to build closures and stuff, and that's kind of painful. But actually, there's also something interesting there to be said about that. And then we'll talk about how you can control data layout. Okay. It turns out we don't need to change the logic. We just need to change its interpretation. And that's also kind of an interesting observation. So I guess I'll see you tomorrow for one last time, one last go around. Okay.